Good morning, trigonometry. It is Mr. Mazzola here coming at you with a brand new video, right? So there'll be two questions posed throughout this video. Question one, question two. So all the Google Form's gonna say. I'll tell you what question one, question two are throughout the video. So make sure you watch till the end. That way we could get that watch time up and we can beat that YouTube algorithm, am I right? Haha. But seriously, make sure you like, comment, subscribe. Make sure if you want to join the Mozilla Math Club, then make sure you ring that bell for notifications, and I'll enter you in for a giveaway of $50,000 gift card that I'll never give. Anyway, yeah. So today's video is going to be going over something I nerd out about all the time. Waves. So I got a few formulae on the board, as you can see. Obviously, we haven't touched on a lot of them yet, but this should look somewhat familiar. A cosine omega naught t minus phi plus h, which amplitude, angular frequency, which I think we just called b for so far, phase shift phi, and h being the initial height. Same thing with the sine wave. And actually, it could be even more generalized than this bottom one, which we're not going to get to this semester. But in fact, you can actually have functions of more than one variable once you get to higher level math and or physics. So y of x of t. And it's kind of weird to think about. It's like a three-dimensional wave almost, where it goes with time and it goes with the displacement x and the force. So that's later on in your career. But there's also some other formula I have on the board that may or may not be visible, but we'll see. Purple doesn't show up well on this chalkboard, but yeah, so this is frequency. Frequency is 1 over t, big T, which is period. Remember what period is, which is 2 pi over that b, or omega naught over 2 pi. Now, we touched on omega before, that W-looking thing, right? All the way back in that circular motion. And it's coming back, and it's actually the exact same variable, only this time around, since we got a little bit more trig under our belt, we know that this is more than just angular speed. In fact, it's angular frequency too, as we're going to touch on later. And then there's the next one, which is velocity v, or speed v, which is lambda over t. That lambda looking thing, it looks like an x, that's a lambda. It stands for wavelength. So how long the wave is. So given a regular sine graph, it's from peak to peak. So it's that length. And I know we use that to kind of adjust the period, but once we get to actual like physical waves, which is what we're going to do in chapter 9.8, which is simple harmonic oscillators or simple harmonic motion, that's going to be what we have in store. But that's also known as lambda times f, which is your regular frequency. And then here I got a, oh, you definitely can't see that, but it is the velocity of the wave. It's a propagating wave. And it's actually used for music and stuff. So like velocity of the wave is equal to the square root of, this is called the force of tension in the string over your mass density, which is mass over length of the string. So the mass of the string over the length of the string, which is kind of cool. So just a little bit nerdy thing, but here's a little throwback Thursday. Remember that formula from your first test, which was velocity is r omega, or speed is r omega? That may come in handy, only this time we don't have an r, because r is radius of a circle, right? Now we're dealing with waves. Is that the same thing? That's up for you to decide. Hint, hint. So I want to first ask you a question. Let's do question one right off the get-go, all right? And then I'll give you question two later on. So your question one today is, what relationship, so you can't use this one, cannot. So we've already discussed that V is equal to R omega. So that's an R right there, but somehow I got, there we go. R omega. What relationship does V and omega have with waves? In other words, investigate. How do you get V to equal omega and omega to equal V? And I want you to research this, look it up, look at wave equations and stuff like that. And I want you just to kind of investigate. I want you to write about 2 or 3 sentences about your findings, and make sure you sign it too at the end, like put your name there. That way I could take attendance. That's how you take attendance on AMI. So that's going to be question 1, and it's going to be on a Google form. It just says question 1. So your question 1 in trigonometry is, what relationship does V and omega have in waves? Not in circles, because we already investigated the circle one, but waves. All right, and now question 2 will come in a little bit later, but I want to kind of nerd out, and I know, right? I always do this. However, this stuff is really cool, and I always find it very fascinating. And the stuff I'm teaching you is actually useful, like argue all you want, pre-calc algebra. Some of that stuff is not necessarily useful everyday life, but this is. So let's investigate why I'm so excited about this unit. So when you're producing sound or in light or any type of wave, right, there's this dissonance that may occur. For example, if you're in, let's say, concert hall, let me try to give you a visualization, and don't make fun of my drawing. But let's say you're in a concert hall, right, and you're playing violin or something. I don't know what you play, so let me see right here. That's you. Let me draw this beautiful little. Right, and then here's scroll. That's a violin, and you're playing your favorite song. It could be anything. It could be Canon and D. It could be Super Bass by Nicki Minaj. You know, the usuals that you play at concerts. And then when you're making music or when you're producing sound, you can use things called waves, like this, boom, boom. And in fact, there's sine waves and cosine waves of stuff we've been graphing, only they look more complicated, look like this. But we've been trying to just do the basics so far. And it's producing sound. And it doesn't produce sound in just one propagation. It produces sound 360, unless you're putting it through a vacuum or you're putting your sound or whatever wave through some sort of tube, right? Now, when you do that, because a concert hall is technically a really, really, really big tube, there's going to be some bouncing around. So it's not just going to stop and absorb when it hits like a wall or anything. It's going to bounce back and everything. And there are these places in the concert hall that are very specifically kind of already engineered out to where clients can't really sit there, because there are these things called dead spots. Now, here's where things get cool. When everything's bounced off, now, I'm just going to put an example over here. Let's say, and this is just one of the waves, one of the infinitely many waves. And let's say this is the wall, right? And the wave is coming in. It's propagated already like this. And then it bounces off. And it bounces off in such a way to where it actually perfectly, every time there is a peak, there was another minimum. And in such a way to where, if this is the x-axis, let's say right in the middle, and you were to average them out, meaning this, then this would cancel. And then this wave would cancel. And this wave would cancel. And for that exact second, there's going to be no sound, just silence. That's called a dead spot, meaning like your ears can't perceive those, because there's this very specific principle called the principle of superposition. And that's when, if you got two waves, let's say sine of x, let's kind of look at that, where it starts at 0, right? And you got, let's say, 2 sine of x, so that means the amplitude's at, now let's do 3. Let's do a prime number. Yeah, well, 2 is a prime number, but yeah, 3 sine of x. And then you got so amplitude 3, and then you got just regular cosine x, right? Where it starts at 1, right? And it's got an amplitude 1, so all the way over here already. And they're graphed on top of each other. Oh, I can't get this perfect, can I? Oh, maybe. Let's see. So it starts at 1, and then every time there's a peak, there's going to be now a minimum, and so it's going to be exactly a phase shift off. So, and then you get to add them together, and that makes one big wave, meaning that this is called the principle of superposition. So, principle of superposition. And then graphing it on top of one another, 3 sine x plus cosine x, if you're to graph it all into one big wave, you just get to add the waves together, and their amplitudes kind of stack on top of each other, superpose each other, if you will. So it'll start at 1, and then that next part is going to be at 3, so it's going to look like a really wacky wave. And that's kind of what I did my research on, is it's called a Fourier transformation, where you just stack a whole bunch of sums of, you add up a bunch of sine and cosine waves together to make it look like what you want. And it's possible, especially if you have a periodic motion. And sound's periodic, right? Light's periodic. Everything has a period if you really think about it. Like your heartbeat, by definition, beats at a very specific rate, a pulse rate. So that's got a period as well. So anything that has a period in it, you're able to use sine and cosine waves to model it and superpose them on top of each other. And I just find that stuff fascinating. And here's going to be question 2, by the way. Question 2, your job is to, speaking of concerts, what is a dream concert you'd love to go to and why? So, for example, my dream concert would be go to Green Day, because I love Green Day. That's my favorite band. Or the 1975, that's also a great band too. Or go back in time and see Rush in their prime. I think that'd be such a cool concert to go to. Anyway, that's your second question. But once we get to simple harmonic motion 9.8, so that's the last section of this chapter, we still have 9.4 to go through, which is graphing tangent, cosecant, secant, and cotangent, which we're only going to scratch the surface on because, in my opinion, I think the sine and cosine wave stuff is important. And it's just good to be familiar with the other 4. But we're not going to go nearly as much in depth as we are with sine and cosine. But make sure you finish your assignments. I know there's a lot of assignments. I'll try to update the gradebook today. But answer question 1, answer question 2. Make sure you sign off on those questions as well in the Google form so I can take attendance. And good luck. Email me with any questions, and I will see you tomorrow.